is based on the idea that the energy in the universe is constant. So there's two very important pieces of information here, and that is the change in the energy of the universe is zero. This is the law of conservation of energy, or the first law of thermodynamics. You probably talked about this in physics, right?
We did that in biology.
In biology as well? Huh. So, the energy of the universe is equal to your energy of your system and the energy in your surroundings. Right? Total energy is the energy you're either in the system or you're in the surroundings. There's nowhere else, remember? Because our universe is a box. You've got the system, and you've got the surroundings. So, if this quantity is zero, the change in energy of the surroundings is equal to the change in energy of the system, but one of them is negative. All that negative sign means is that the energy is going in a different direction, basically. So the quantity of these two values is the same. The quantity of energy is the same. The negative sign says what's happening is one is moving into the other. So it goes out of one into the other. So it either moves out of the system into the surroundings or from the surroundings into the system. Enthalpy is basically the energy of the system. So enthalpy is the energy content of the system. So enthalpy is the energy content of the system. So basically the potential energy that's there available to do the work. However, we can't measure enthalpy. What we can do is measure the change in enthalpy. We know what it was. We don't know exactly what it was before or after, but we have developed ways in order to measure the difference from the start to the finish. And it turns out it doesn't matter how you change it. It doesn't matter if you change it in one step or 3 steps. All it matters is it got from point A to point B. So if Brock started here in this corner and ended up in that corner, Matt did too, but they took 2 different ways to get there. The total enthalpy change would be the same because they started in the same spot, ended in the same spot. But Brock could have gone between the tables, Matt could have jumped over them and done twirls and hop, skipped, and jumped over there, but the total energy change would be the same because they went from the same point to the same point.
So you wouldn't know got there, just like that you
Just that you got
from
there.
one place to another.
Yeah. So you're going to find there's many different ways to actually figure out enthalpy change. So we're going to figure out how to determine enthalpy changes, and then you're going to use the different ways to figure it out for a reaction. So if this is now delta H, and we talked about the energy of the surroundings yesterday, Q, we get the most important connection, and that is negative Q is equal to delta H, or Q is equal to negative delta H. Either one works. But the energy of your surroundings is equal to the change in energy. Sorry, the change in energy of your surroundings is equal to the change in energy of your system. So the amount of energy absorbed to melt it comes from the room, and it's just going to be the amount of energy that the air around it changed. To change this chemical equation to a thermochemical equation, we would have to put an energy on the reactant side of our equation. So energy plus the ice cube will make liquid water. We'll also be able to represent it H2O solid goes to H2O liquid, and there's a delta H change, and it's positive. So we're going to get into this probably next week, but there's going to be two ways to represent energy changes in a thermochemical equation. So again, it's not a balanced chemical equation, or your delta H is negative. So your endothermic reactions will have a positive delta H. Your exothermic reactions will have a negative delta H.